Greetings, girl, and welcome to my world of phrasing right up to bat. It's the Daisy Age, and you're about to walk top stage. So,
hi guys, my name is Nako Nakatsuka. I'm a fourth-year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So now we enter a chapter talking about atoms and the quantum world, and we're going to start out by talking about the properties of light, which is all around us. And so here you can see the electromagnetic spectrum. And as you can guess, electromagnetic radiation is a combination of the waves of electric and magnetic fields. So if you look at this diagram right here, you can see the electric fields in blue in one direction, and then the magnetic field that's perpendicular in red to that electric field. So the fields oscillate in a direction at a certain strength with a frequency written as mu. So this is frequency. And the unit of frequency is per second, also written as second to the power of -1. So the electric field pushes on charged particles, causing them to oscillate. And the frequency determines the position in the electromagnetic spectrum. So as you can see from this diagram, at low frequencies, such as 10 to the power of 4, we have radio waves. And then as the frequency increases and the distance between each wave, or the wavelength, gets smaller and smaller and smaller and smaller, up until we get to 10 to the power of 20, which is high frequency, we get different waveforms such as gamma rays, X-rays, UV rays. And in the visible range right here is where we can see different colors. So for example, when an electric field oscillates at around 6.4 times 10 to the power of 14 hertz, or seconds to the power of -1, so this can also be written as hertz, which is the unit that is used right here. That fits in right around here, and we see the color blue. On the other hand, if an electric field oscillates at 4.3 times 10 to the power of 14, we see red, which is closer over here. So electromagnetic radiation is also characterized by peak-to-peak distance, which is called the wavelength. And as you can see from this diagram, it's from the peak of one wave to the other. So on here, I can also show you guys that the wavelength is like so, and it's given the Greek letter lambda. Okay, so going from low frequencies, such as when we talk about buildings, humans, basically the macro scale world, to higher frequencies on the electromagnetic spectrum, such as atomic nuclei and atoms and molecules, this is the range that we're going to talk about the most in Chemistry 14A. So another thing that we need to talk about is the speed of light. The speed of light is written as c. And we can actually derive a relationship between the speed of light, the frequency, as well as the wavelength. Because the wavelength, lambda, is the distance between two wave peaks, right? So it's going to be in units of meters. And speed is in meters per second. So you can already guess what this equation is going to look like. It's that the speed of light is lambda, or the wavelength, multiplied by the frequency. And this is always a value of 3 times 10 to the power of 8 meters per second in a vacuum. So this is a constant, and this equation is something that you'll have to know. So this is the classical mechanics description of light. But now we're going to move into more of the quantum mechanics. The reason for this is because classical mechanics only explains the behavior of large objects. So for example, when we talk about Newtonian stuff, we talk about force is mass times acceleration, and that shows no restrictions on values that may have a continuous function. But quantum mechanics is needed to describe the behavior of very small objects that can accept energy only in discrete amounts called quanta. So quanta is the discrete amount of energy values that very small objects can accept. Quantum in Latin actually means how much. So to give a very brief example, if water is poured from a bucket, that can be described by classical mechanics, and it appears to be a continuous fluid, right? You just open the faucet, water comes out, it looks like just a continuous flow. But if we have a very sensitive experiment conducted, we would be able to see that the smallest transferable unit is actually one discrete water molecule. So these tiny, tiny, tiny water molecules, which we're talking about the molecular level, makes up the macro scale such as water. But now we need to talk about this tiny, tiny scale in order to understand light. So quantum mechanics basically describes light in that it absorbs and it's absorbed and emitted in discrete units called quanta or photons. So now we'll get a little more into that.
May I cut this dance to introduce myself as the chosen one to speak. Let me lay my hand across yours.